Hi folks, so today I'm going to be taking you through the ionization energy and recapping some of the trends that you learned in higher chemistry. So if you want to learn about advanced higher ionization energy, please keep watching. Well, what is ionization energy? So this is something that you would have learned from higher. Ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. So that is something that you would have learned in higher chemistry. It's something that you could have been asked to write the definition of, so hopefully that is familiar from you. And here's a couple of examples of what the first ionization energy looks like. So you've got your electron, or your atom as a gas, and that's how you write your first one. And then with your second one, you're removing a second electron. Now this is in the data book, so this E gas equation is in the data book, so you don't need to worry about memorising it. It is there for you to use as an example. So here is 3 examples of what you learn in higher chemistry. We'll start with our atomic size. Here we go. So if you have a bigger atom, what that means is the outer electrons are going to be further away from the nucleus, so they're not really going to feel the effect of the nucleus of that positive charge. So ionization energy decreases with your atom size. Let's have a look here at nuclear charge. So the more protons that you have in that nucleus, you're going to have a bigger positive charge. What that means is it's going to pull the electrons closer to your nucleus. So the more protons you have, so i.e. the kind of higher the atomic number, the more pull it's going to have on those electrons. So what that means is it increases your ionization energy. And finally, let's have a look at electron shielding. So what that means is electrons can be shielded from outer electrons can be shielded from that inner positive charge, so they won't feel the full effect of your positive charge. So if you have more energy shells, what that means is those further out electrons aren't going to feel the effect of your positive nucleus, so the ionization energy is going to be lower in this case. Let's have a look at some examples. So noble gases have the highest first ionization energy. You would have been able to tell me this in higher. You would have said that it would have had a filled subshell, which was a particularly stable electron arrangement, and it meant that it was hard to remove an electron. Well, in actual fact, yes, that is correct, but specifically it's because they have a full set of p orbital, and having that filled set of orbital is a very stable arrangement. You know, as we had a look from our electronic configuration of ions with copper, wanting a filled set of d orbital. That's why in particular noble gases have your highest ionization energies, because that filled p subshell. Also, there's a decrease this time going from beryllium to boron, so that is the very top of the periodic table going across the way. Feel free to grab one just to have a look at where I'm talking about. And the reason for that is because with beryllium it has a completely filled 2s orbital. And a filled 2s orbital, or just really a filled orbital in general, is a particularly high it's a particularly high value. It's something that every electron really wants to do. So because it is completely filled, it is very stable. So what that means is it's starting to get easier to remove electrons from beryllium all the way to boron, and that's because of it's easy to remove a 2p orbital, a 2p electron from your boron, because there's only 1 electron in that p orbital. There's also a decrease as well going from nitrogen to oxygen, and the reason for that is if we have a look at nitrogen's electron arrangement, it is 1s2, 2s2, 2p3. Now your p orbital can hold 6 electrons, so that is a half filled outer p orbital, and again that is relatively stable. Like if we go back to our electron arrangement of ions, if you have a look at chromium, it has a half-filled D subshell, and again that's relatively stable. This is the same thing here, so that's why it gets slightly easier to remove an electron going towards oxygen, because it doesn't have that half-filled stability. And then finally, if you have a look at your transition metals, so we spend a lot more detail on transition metals further on in organic chemistry, so don't worry too much about it. So going from scandium through to zinc, again grab a periodic table. They're relatively similar, and that's because our 4s electron are taken out first, so the 4s fills before the 3d and it also empties before the 3d. So that means that it's a relatively similar value to remove all the transition metals, certainly from that first row. There is a slightly different exception, and that's because of zinc. It's because it is got a filled 3d and 4s, so everything's completely filled. That's why it's slightly higher than the rest of the other transition metals. And that's us finished ionisation energy for advanced higher chemistry. In actual fact, that's us finished the very first book as well of inorganic chemistry. Hopefully that has been useful for you, and I'll see you in the next book, which is orbital shapes.